Allora, ladies and gentlemen, please welcome to our first live event in this page. Tonight, I have the honor to host Professor Guzzo, an astrophysics teacher in the University of Milan. I'm very happy to that Professor Guzzo accepted my invitation because it is correct to the goal of this page. That is to introduce in your mind astronomical and scientific topics. Tonight, we will talk about the expansion of the universe. Before I give the word to my friend Giovanni Granat, I have to remark two important things. The first is that this event is sponsored by UDC, the most important representative list in the University of Milan, without the help of UDC, this event couldn't be done. The second one is that we will broadcast this event also in YouTube, so don't worry if you lose this live. Don't worry. So enjoy the lecture, and I give the word to Guzzo. Bye.
Good evening, everyone, and thank you, Gerd. Thank you, Professor Guzzo, for being here. And thanks to Free Astro Science and to UNICI, which I advise you to visit both pages on Facebook or Instagram. They both helped us to make this event possible. Of course, the first thank you is for Gerd and for Professor Guzzo, but they were also quite important in making this event possible. So Luigi Guzzo is a full professor of astrophysics at University of Milan. He's a very important expert in cosmology and especially the study of the growth of large structures from primordial density fluctuations. He's been leading and he will lead important missions on the topic like Vipers, Dark Light, or Euclid. And he is here tonight to guide us in an introduction to the expansion of the universe, one of the most important and puzzling questions of cosmology, about which we know a bit more today, but there is still a lot to learn. And he'll introduce us to the topic starting from the very beginning and with a very clear vision, which I hope all of you will be able to follow anyway. For any questions, use our chats on the two Facebook pages. I'll try to read all the questions that come and ask them to Professor Guzzo at the end. So I'll thank him again and happily leave him the floor for the talk.
Okay, thank you, Giovanni. And yes, I'm sharing. Okay, you have to allow me to share the screen.
Yes.
I at the moment I cannot.
Now you should be able to.
Yes, I can. Thank you. Yes, and now I start. Can you see the slide?
Yes.
Yes, and you can also see my mouse, right? My pointer. Fine. Okay, so first of all, apologies about the slides in Italian. I will talk in English. Well, normally my popular conferences are in Italian, and so this is why the slides are in Italian. Anyway, I speak in English, and so you can certainly guess from my words what is in the slides, what's written in the slide. There will not be many words in the slides anyway. Okay, so good evening, everybody. So tonight I was asked by Gerd to give some overview of what do we know about the expansion of the universe. And the title of this conference is The Enigma of the Expansion of the Universe. And why an enigma? Well, the enigma is that we don't completely understand why the universe expands, or in particular, we don't understand why its expansion rate, so the speed of this expansion is not going the way we naively thought a few years ago. Okay, so something happened about 20 years ago, and we realized that this expansion is not behaving the way we thought. So we're going to go through this very exciting story, and you will see that there are still many things to discover in the universe, so that people can make discoveries also in our time and get the Nobel Prize for that. So the Nobel Prize 2011 was given to these three people for the discovery of cosmic acceleration. This was the justification that was given in the official statement by the Nobel Committee in Stockholm to justify why the Nobel Prize was given to these three persons. And basically Sol Perlmutter and Brian Schmidt were leading two groups which using a similar method arrived to the same conclusion more or less at the same time. So they arrived to the conclusion that the universe today is not only expanding, but is expanding with an accelerated expansion, contrary to what one would naively think. And I will try to explain you why we would think that the universe should actually break, should decelerate, so should reduce the velocity of its expansion speed. And but to understand this, we have to go a little bit back in time and try to understand where all this began. So when, first of all, we understood that the universe was actually not static, something pretty surprising if you think. It's not at all obvious or normal that the universe around us, all the galaxies, should be expanding and receding from us at a speed that depends on the distance. And so again, you know, as in all epochs of humankind, understanding the universe meant understanding what's, what the universe is at the time we look at it. You know, at the time when people didn't quite understand even the way the planets were moving around us or around the sun, who knows? They thought that we're going around us, not around the sun. And so that was the universe. So cosmology at the time when this picture was painted was basically to understand the solar system. Okay. Today, cosmology means understanding our universe. So our universe today is much larger. Our universe is made of we now know is made of billions of galaxies, and each galaxy is composed by 100 of billion of stars. And so what we are going to do today is to use galaxies very much like building blocks. So the units of what the universe is made of. There is something else as well. There is a lot of many other things, but galaxies are helpful, are useful, as I'll show you. This is also my personal perspective, because this is the area where I work, is the area of using galaxies to trace the large-scale structure of the universe. And the large-scale structure of the universe that we see today is actually reflecting a lot of what happened in the past. Okay, so the universe today is like it is because it started from some initial conditions. It went through a number of events. And if the universe were different, if the universe contains, for example, less matter or more matter, then we would see a different structure, for example. Anyway, but let's go one step at a time. And, you know, today, as I said, doing cosmology means going out of our galaxy and use our galaxy just like one little brick of this huge construction that is the universe. And so our galaxy, what is it? Our galaxy is our home. What we see if we are lucky to live in a place with a sky that is sufficiently dark to see the Milky Way, okay, which is what is in this picture. This is a beautiful picture taken at the European Southern Observatory in Chile, where at night the sky is really dark. It's so dark that you have the impression that the stars project a shadow on the ground when you are outside. It's absolutely amazing. We cannot have this kind of darkness in our country. Perhaps if you have been lucky to go to some isolated place on the mountains, you had the fortune to see the Milky Way. So this white band on the sky, what is it? Well, this is our home. That is the concentration of stars that you see when you look through a disk in which we are embedded. It's like we are sitting on a little piece of chocolate inside a cake. And we look through the cake and we see a lot of pieces. And if you look outside the cake, we see very little. So this stripe that you see on the sky is actually like a disk that we are looking through, okay? And this became clear when we were able to look outside, to look far away with our telescopes and see things like this. This is a galaxy which is probably very close to our own galaxy. So we are staying inside one of these systems, somewhere like here where I put my pointer. So we are in a peripheral branch of a spiral. You know, this is one of the types of galaxies you can find in the universe, a spiral galaxy. Galaxies where you still have gas, you still have star formation. Stars are being formed in all these regions that you see here. All these red regions are clouds of hydrogen that get ionized, so they get heated by new stars, by very, very hot stars that emit UV radiation and excite the gas around them. So we are inside one of these. So we are going out of this system. We are using these systems as little points around the universe to see how they are distributed, understand, hopefully, the distribution of matter around the universe. So if you look around and you look away, the largest, I mean, the nearest spiral galaxy, the nearest big galaxy, so the nearest galaxy which looks a bit like ours is M31, the Andromeda galaxy. That's about 2 million light years from us. It's basically very nearby in astronomical terms. 2 million light years is really a short distance, although it would take 2 million years to travel there if we were able to go at the speed of light. So it's not close in human terms, but it's very close in cosmological terms, in astronomical terms. Anyway, if you go further, you look around, you realize that galaxies are not distributed randomly. Galaxies tend to cluster. They tend to, again, gravity, on these scales, gravity is the dominant force. And so galaxies assemble, they assemble in clusters, they assemble in groups, a few galaxies, they assemble in clusters. We call clusters concentrations of hundreds, thousands of galaxies, like the one you see in this image. And more in general, they tend to cluster on even larger scales, and I will show you some examples in the following. However, if you go to sufficiently large scales, and you make a map like this, for example, okay, what is this? Well, this is a map. It's quite an old map. It's a map from the 1990s, so it's 30 years old. Still, it's very useful to explain what I want to explain. This is a photographic atlas, so it's a mosaic of photographic plates. So photos, very large photos that are large as, like this, okay? Like I'm doing it 6 degrees by 6 degrees. And with the telescope placed in Australia, at that time, they covered the whole southern sky, made an atlas of pictures of the whole sky. And this is the result of analyzing all these pictures with a machine that was able to digitize those plates, because those were not digitized. Today we are used to digital images. Our telephone takes digital images. Well, this was not the case at the time. There were already digital detectors, CCDs, exactly like those that we use now in the telephones. But if you wanted to have large areas, you could not use CCDs. CCDs were very small. You could not map the whole sky using CCD. It would have taken 100 years at the time. Today, not. Today, there are CCD arrays that cover several square degrees at once, but not at the time. So it was a time when photographic plates were still useful. Anyway, the key point here is that from this sort of photographic atlas, people, especially the Cambridge group, this comes from a group in Cambridge, George Statue and his collaborators, made a search for all galaxies down to a certain distance in these photos, and build a big catalog, including only the galaxies. So throwing away the stars that were nearby from our galaxy. And then they built this map, and this map shows you the level of concentration of galaxies inside the little cells of a given size. And using colors, they coded the amount of concentration. So essentially, how many galaxies are in each cell. Where you see white, it means that there are many galaxies. Where you see brown, it means that there are very few galaxies. Of course, these black dots are not low density places, but are just places where there was a problem in the plates, or there was a bright star, for example, and so they had to be cut out of the map. So they are empty regions, they are not low density regions. Low density regions are like this, high density regions are like this. So what does it mean? Well, it means that, for example, the cluster that I showed you here is probably something like this. Okay, this is one, this is another one here, another one there, other here, other there, other there, other there. So there is structure. You see structure even in projection on the sky. Okay, this goes to a certain depth. So it's basically showing you the structure over a certain depth. However, if you take a sufficiently large area, like an area like the one I'm circling with my mouse, you can say that the universe looks a bit the same in every direction. Of course, if you look here, you find a lot of galaxies. If you look here, you find fewer galaxies. Okay, but if you go here, you find many galaxies here and less galaxies here, or here. Okay, so this means that if you average over sufficiently large scales, then the universe seems to be the same everywhere. Okay, and so this has been taken as a paradigm, as a principle, and took the name of the cosmological principle. So basically this is translated into saying that the universe is the same in every directions we look. And if you add to this that we are not sitting in a spatial place of the universe, which is a very natural assumption, it's a kind of Copernican principle taken to cosmological scales, then you conclude that the universe is homogeneous and isotropic. So the same in every place, same average density in every place, and the same wherever you look. This is very useful because if you take this principle and you plug it in, so you add this prescription into the theory of gravity, and the theory of gravity we use today since the beginning of the last century is Albert Einstein's general relativity, which describes completely all the effects that we have measured from gravity, including those that Newtonian gravity, so the theory of gravity that we had before Einstein, was not able to describe. For example, the fact that not only planets or masses are attracted by a planet, by a mass, but also light. So light is deflected by the presence of a mass, something that Newton's theory is not able to predict, because Newton's theory doesn't include any prescription for objects without mass, like photons. So when a few years after publishing the theory of gravity, the theory of general relativity, Einstein himself tried to apply the theory to the whole universe, so to a distribution of mass which was described by a homogeneous and isotropic density field, and he got from this some indications, some consequences for the geometry and for the dynamics of the universe, for the kinematics of the universe, to be honest. That is, depending on how mass there is inside the universe, the geometry of the universe was more similar to a sphere or to a flat plane, or to something stranger like a saddle. At the same time, there was evidence that the universe was unstable. Actually, if you leave a distribution of mass there by its own, since the mass attracts itself, this either contracts. If you leave it there with zero initial velocity, will contract. Otherwise, you can put it in motion and then it will expand. So it will be very difficult to keep it steady. And this bothered a bit Einstein, but he did some. He added some constant to his equations to solve this. But then there was another piece of the puzzle that was coming up from the observations. We talked about the theory, but the observations were observational astronomy was coming up, and in particular, people using larger telescopes had started measuring galaxies in some way, observing galaxies in some way, and getting some important information from the most nearby galaxies, from the most, the brighter galaxies on the sky. And these people were, different people. The one who is most remembered is Edwin Hubble, but there were people who contributed to this almost equally. Hubble had the ability to put together measurements from other people, add new measurements, and derive a coherent picture, and propose a new paradigm. What is this paradigm? Well, essentially, what these people were doing was to take galaxies as the one I showed you before, very luminous galaxies. So some galaxies that today for us are very close, are easy to observe. Well, at the time you needed many hours of telescope to measure what we call a spectrum. Okay, what is a spectrum? A spectrum is nothing else than a rainbow. So you get the light from the galaxy, and you send it through a dispersing element, something that produces, separates the light into its color components. So in a more scientific way, into its wavelength component, its chromatic components. And why is that? Well, because if you do this, you see very interesting features in the spectra. And this is what you can see in this cartoon. These are realistic spectra. It's a cartoon, but the way that the spectra and the lines have been drawn is quite coherent. And what are the different spectra? Well, the bottom one is the spectrum you can measure from a galaxy which is very nearby, or from a star. Okay, so you have a continuum color. The color you see is continuum going from the blue to the red, and on top of it you have dark bands. Okay, so these are funny. Dark bands means places where you don't get light. Light doesn't arrive, so they're kind of absorbed. Well, this is produced by the atmospheres of stars, and which are absorbing some light from the photosphere emission, which is so to say not the solid part of the star, because the star is not solid, but where you see a surface of the star, and that's where matter is more densely packed. And so if it is densely packed, you get a continuum emission. Okay, and the absorptions are a classical example of what you study when you do quantum physics. These are the evidence that atoms absorb light in selective matter only at specific given wavelengths, and these specific given wavelengths correspond to specific energies, and these are the transition energies that electrons can do inside the atoms. This is pure quantum mechanics at work. And in fact, one of the major experimental evidences from which quantum mechanics was originated was the hydrogen atom. How to explain the lines of the hydrogen atom. And here you see the hydrogen lines. This is a hydrogen line H alpha, which is the result of the transition to level 1 of the electrons, and there is also the series of other lines. This is H beta, and all the other lines are here. And then there are lines from other elements. In particular, for example, these two lines. Here you don't see that they are two lines, but here you see they are two. These are the same calcium lines. Anyway, so they are lines that you can recognize in the laboratory. So that's the interesting thing. So there's a lot of information here. First, you can say, well, there are the same elements in the stars, in the galaxies that we have in the laboratory. So we are made of the same thing. That's not trivial. Okay, so the universe is about the same everywhere in terms of elements. But this is not the story here. The story here, which I've kind of skipped around for the moment, is that this spectra that you see look similar but different. What happens and what they are? Well, these are the spectra of more and more distant galaxies. So this galaxy is a bit more distant. This is more distant. This is very distant. Okay, you give the impression of distance by making it smaller and smaller, which is a good approximation to say it's distant. Anyway, and what happens? It happens that you can recognize the same pattern. You can see that these three lines are these three lines, are these three lines, are these three lines. Now you see that this separates. But here, which you can take as the laboratory, they are around 400 nanometers. This is a scale of wavelength, nanometers, okay? But when you go more and more distant, the same lines are seen at larger and larger wavelengths. So this was at 400 and now it's almost at 500. Okay, so what's happening? What's happening here? Well, the first interpretation, the easiest interpretation of this that was made by Hubble is that this is what you expect if the source, which is emitting this radiation, these waves, is moving away from us. Okay, this is the same effect you get, well, this interpretation, because in fact things in reality are going slightly differently, but they can be approximated with this effect. Exactly like when you hear an ambulance with the siren, and the sound of the siren is very different when the ambulance is coming towards you or when it's going away. Okay, so you hear this classic one. Okay, so the pitch of the sound is higher when the car is approaching and is lower when it's going away. So it's bluer when it's approaching and it's redder as here when it's going away. And so the interpretation of this is that the galaxies, the more distant galaxies, were flying away, were expanding, were receding from us at the speed which was larger and larger the more distant they were. So this was the discovery of the expansion of the universe. So Hubble concluded the galaxies were flying away from us, or from each other, with a law which was proportional to the distance. So if you put in a graph, on one axis is the original drawing by Hubble. You put the distance that you have to measure in another way. You have to have a way to measure the distance to these objects, and he had a way. We will come back to this. And on one axis, and on the other axis, you put this velocity that you derive if you interpret this shift of the lines. So you measure the difference between, for example, these two lines. The first of these two lines at this distance with respect to the laboratory position. Okay, so this separation in wavelength gives you a velocity. Okay, if you use this Doppler effect formula, and you put them on a graph, and you see that there is a fairly linear relation. So there is a straight line going through the points. Of course, the points are not on the lines because there are errors, okay, measurement errors. This is typical of physics. And so Hubble derived his famous law. This is the Hubble law, so that the apparent speed of recession is proportional to distance through a constant, and this constant is the famous Hubble law, Hubble constant. We know today that this is not really a velocity, it's the space that is expanding, and so what we measure in the radiation is the difference between the size of the universe, basically when the light was emitted, and the size of the universe today. But this resembles a Doppler effect if you are considering galaxies which are not too distant, okay? So the universe is not static. So Einstein, when he tried to apply general relativity to this simplified distribution as described by the cosmological principle, he found that it was difficult to keep the universe static. Well, and in fact, the universe is not static. So the universe is expanding, and Einstein said, well, basically my cosmological constant is useless. That was a mistake. He threw it away, and so the cosmological constant, so this little piece that he added in the equations to keep it static, was discarded for a while. We will see that it will come back. Anyway, this is Hubble, by the way. And so what this means that the galaxies are receding from each other? Well, it means that if you get the movie, if you rewind your movie, then the galaxies will get closer and closer to each other. And so if you go back enough in time, you must arrive at a moment when everything was in the same place. And this is what we call the Big Bang. And today we know this is very probably located at 13.8 billion years ago. And so quite surprising. Of course, there are many questions that arise now that you know that that galaxies expand, that the universe expand. And the first question is, well, we basically know, we have seen, because Hubble has measured it, how fast the universe expands today. Okay, so the slope of the line of the Hubble relation essentially tells you how quickly the universe is expanding today. But well, my slide says, what do we know about the expansion rate in the past? Well, let's first ask, what can we expect for the expansion rate in the future? It's more interesting, no? Because we are asking what will happen to us, or what will happen to our Earth, our galaxy, in 5 billion years or in 25 billion years, who knows? Well, in other words, will the expansion of the universe continue, or will it stop? Whatever. And this is what is drawn in this figure. Essentially, on the x-axis you have time. When you read now is today. Okay, so this is today, and then the scale is in billion of years. So this 10 billion years, 20 billion years, 30 billion years. And of course, we have no way to go and test the future. Of course, yes, it has to happen still. But we have a way to look into the past, because, astronomers are lucky men, and astronomy is a lucky science, because if we look more distant, you look in the past. So if you make measurements of objects that are located at 10 billion years away from us, you are basically seeing what happened 10 billion years ago. Okay, so Hubble measured essentially the expansion rate today, for using very nearby galaxies. He basically tested the expansion rate in our local universe. But what about if we could look back into the past? Well, these curves that you see here are possible different scenarios that you might encounter. Look at the orange curve. The orange curve is a universe. What do we have on the y-axis? Well, on the y-axis, you can think to have the separation between two galaxies that are expanding, and that today we see expanding, okay, with the velocity that Hubble measured. But these two galaxies can have different behaviors in the future. They can expand and then stop and then come back. And this is what you see in this orange line, okay? This is the separation of the two galaxies, the distance of the two galaxies on the y-axis. So from here, which is today, they will expand a bit more, and then they will stop expanding and will start contracting. So their separation will start to become smaller and smaller and smaller and smaller and smaller. And in this universe, you will have the opposite of a Big Bang. You will have a big crunch. So everything will come back into a point like it was at the time of the Big Bang, okay? And you see that now looking in the past, remember that if you look to this side, you're looking into the past. This kind of universe has one specific property, that it is very young. You see that to go back to zero, when you arrive at zero with the separation, it means that the two objects were together. So the Big Bang was here. So the Big Bang was, in this model, 7 billion years ago. Perhaps it's correct, or it was correct. We know it is not correct, but this is a possibility. To have this universe, you need a universe with a lot of mass, okay? A very dense universe. The mass is sufficient to stop the expansion and make it collapse again, okay? The other lines that you see are other cases in which the density is lower. The green line is a model which is expanding, is breaking, is decelerating, and then it will stop at the infinity, when the time will become infinite. The blue line is an even lower density. That universe will never stop. Will just keep expanding because the density is too low. And the red line is another strange case, which I'm going to talk to you about in a minute, even crazier. Not only you see the universe doesn't collapse, but it seems to expand even faster. So how can we think? So basically what we want to do, what we could do to understand this, is to repeat what Hubble made in the local universe, to repeat it in the distant universe, to repeat it here. Because if you make this measurement here, you will find one of the curves, okay? So in this case, you will not find objects more distant than here, and you immediately know that this probably is not the right model. But here, for example, you can distinguish the three curves depending on the value of the Hubble constant at that time that you measure, okay? So you would measure here or here or here, okay? Well, what is the problem? The problem is that to construct a diagram like the one Hubble built, you need to have some object for which you can know the distance, and you can measure the redshift, the shift of the lines in the spectrum. But to measure the distance, how do you measure the distance of an object on the sky? That's the oldest problem of astronomy. You have a lot of objects on the sky. You don't know at which distance they are. You see a star. You don't know if it is a bright star, which is very nearby, or is a faint star. Sorry, it's a bright star that is far away, or it's just a faint star that is very nearby and you see it bright, okay? And so let's take a look at how did Hubble measure distances, okay? I told you that he measured spectra, so he measured the shift, and he measured the distance of these objects. Well, he used some specific stars inside these galaxies. Okay, I told you that he looked at galaxies which were relatively nearby. Well, you could recognize some special stars inside these galaxies. These stars are called Cepheids, okay, and have a special property that they fluctuate. So their luminosity goes up and down regularly, because they are going through a special phase of their evolution in which there is no clear equilibrium between gravity that contracts the star and the pressure produced by the thermonuclear reactions that makes it expand. And so they go up and down for a long time. And the good thing is that the period of this oscillation is proportional to luminosity. So the more luminous stars of this kind, they have a longer period. The less luminous, intrinsically less luminous, have a shorter period. And so you can calibrate, they were able to calibrate this right before Hubble used them, and they found a way to associate the oscillation period that you can measure wherever the star is. If you can see the star and you measure the period of oscillation, you don't need to know the distance. So you measure the period, you know the relation, okay, the relation between period and luminosity. Now you have a luminosity. You know that star intrinsically has such luminosity. It's like you say, oh, I have a lamp, I have a bulb, a lamp, which is 100 watts. Okay, I know it's 100 watts. And you tell your friend, go away, go distant with this lamp, and show me this lamp. And then you see this lamp from your place, and you measure the flux that you get from this lamp. So you measure its apparent luminosity. Well, you know it's 100 watts. You measure the apparent luminosity. The ratio of these two is giving you basically the distance your friend is squared. Okay, so this is the same thing. So you find out the intrinsic luminosity of Seyfits, and you know, because you have calibrated it, the intrinsic luminosity. You measure the apparent luminosity and you get the distance, okay? But these stars cannot be used at the distance we want to go. We want to go to distances where we see the difference between our models. We'll never be able to measure single stars in our galaxy. What do we do then? Well, this was impossible until the 1990s. 1990s, people realized that a class of very luminous stars, those stars that are called supernovae. So one of the ways that stars can die at the end of their life is to explode into a supernova. And well, the classic supernovas are thermonuclear supernovas, in which a single star is going through a critical phase of its evolution after having burned hydrogen. It goes to helium, and then there are a series of processes. We are not going to talk about this tonight. But then there is another class, which are called type 1a, okay? And these apparently are quite special, and we think these are double systems made by a very small, compact star called a white dwarf, orbiting a normal star. And this white dwarf accretes gas from the big companion and grows and grows and grows and grows. And at some point, it reaches a critical mass, which is called the Chandrasekhar mass, which is about 1.4 times the mass of the sun. And then at that critical mass, there is a breakdown, and boom, everything explodes. And the fact that this happens always at the same mass or close to the same mass makes these stars to explode with almost always the same luminosity. And this was realized. It's not exactly like this. You need to calibrate this in the sense that, as you see in this picture on the right, here you have the time in days, and here we have the luminosity. So these curves are what are called the light curves. Light curves because this object, boom, explodes, and the luminosity rises, it gets to a minimum and then goes down. Well, at some point during the 1990s, people realized that the brighter supernovae, so type 1a supernovae, were actually lasting longer. So they found a relation to calibrate this and put all stars that you see on the bottom on the same scale. At that point, you had a way to use this as standard candles, like the stars, the Cepheids that Hubble used. The big difference, as you see from this picture here, is that the peak luminosity, the peak magnitude of these stars is comparable to the magnitude of a single galaxy. So these stars, when it explodes, so this binary system, it gets so bright that overshadows the galaxies where it's sitting in. You know, it becomes brighter than 100 billion stars, because a galaxy typically has 100 billion stars. So anyway, so the good news was that there was something that could be used to measure distances very, very, very far away, which is exactly where people were wanted to go and measure the Hubble diagram again. And so there were two campaigns that started to find this kind of objects, and now it's almost time to finish, but I will go a bit faster. And this produced diagram like this, and diagram like this is like looking at the history of the universe, like you look at the age of a tree, and you realize that the rings of your tree actually going to the past are actually behaving differently from what you see today. And people realize that actually, contrary to expectations, the universe in the past had expanded more slowly than today, which was completely unexpected. You know, people were expecting that, I mean, the universe starts with the Big Bang, boom. And then since it contains matter, it has to decelerate because matter produces gravity, and so should act as a brake on the universe. The question was more, is this brake enough to stop the expansion and then recollapse the universe, or the brake is just not enough and the universe will keep expanding forever, but still decelerating, okay? No, what was found is basically that the universe, about half the life of its, about midway between the Big Bang and today, after starting to decelerate, it restarted expanding. And so the curve that describes the expansion is actually the red curve, the one that I was telling you that it was a bit strange. And this is exactly the accelerated expansion of the Nobel Prize 2011 to these people, because these people were those that led these two projects that in 1998 published these results, showing that the universe apparently was not only expanding, but it was accelerating today. So what does this mean? Well, this implies that in the equations that describe the universe, in fact, in Einstein equation, you need to insert again the famous constant that he added, so this lambda cosmological constant, and you have to add it with a magnitude, with a value that is larger than the one that Einstein used. Einstein put the value that was good to stabilize the universe, but actually what we see is that this lambda is larger and actually introduces this repulsive energy. So basically these observations, what we call the lambda, this cosmological constant, implies the existence of this this kind of repulsive energy, what we call also dark energy. Okay, so we call dark what we don't understand. We see the behavior, we don't know what it is. It's in the equations. It's a kind of zero point energy of the universe. So the energy budget of the universe today is therefore dominated by this dark energy. We didn't talk about dark matter tonight, but that's actually the other necessary ingredient of our standard model. Again, something that we are not able to observe. That's becoming embarrassing, I have to say. And our normal matter, the one we are all made of, and what we have in our everywhere here, it's only 4%. That's a bit depressing, isn't it? So this is a model with many dark sides, as you see. Okay, the trouble is that it works beautifully. This model explains everything we see in the universe with very few parameters, and so it's very hard to think that it's wrong. But you know, for example, it explains how you can how you can produce these maps. So how the galaxies are distributed. In particular, here you see galaxies projected on the sky. You can use the Hubble law to derive these distances. In other words, to derive the redshifts and use the redshift as an indication of an approximate indication of their distance. The good thing is that it's easier to measure the redshift than to measure intrinsically the distances. So you can take telescopes, and here we see a little bit, a few nice pictures. Just to relax, we are now near to the end. This is the ESO observatory in Cerro Paranal, in the very north of Chile. That's where the Very Large Telescope sits. This is one of the 4 telescopes forming the Very Large Telescope array. Each of these telescopes has a mirror inside, which is 8-meter diameter. It's still the largest telescope in the world. And so you can take a field of galaxies like this, and with some dedicated spectrograph, again, rather than taking one spectrum at a time as Hubble did, you can take many. So you can take galaxies like this, take your spectrum and produce this kind of pictures. Each of these is a spectrum. So each of these this is the light from one of these galaxies that you see here, very faint. And there is a line in emission here, and this tells you the redshift of that galaxy, and so basically the distance. And so this projected on the sky, where you have the impression that you have a structure, can become a diagram which goes in depth. Okay, so here we are sitting here at 0, and we are looking away, and you can build these very deep probes, and you see inside, I will show you better in a minute, the structures described by the galaxies. And if I take these 2 cones and I put it in this way, you can see better. These are about 90,000 galaxies, and we are, you see down, this is located between 5 and 8 billion light years from us. And you see how the galaxies are distributed. You see there are void regions which are underdense, as similar to what we are seeing in projection, but now this is 3-dimensional, and so there is much more information. You don't have the projection. And why I was telling you that we trust this model? Well, because the model is capable to produce this, and it's quite amazing. We can take our model and all the predictions that have been produced from that model, and the way the model tells us that the universe expands, how much matter, etc., and build and put everything into a computer that can reproduce gravity. And here you see something that it looked like homogeneous, but now gravity is working. Actually, this box is expanding with the universe, so we see it fixed, but it's in fact expanding. And you see that the gravity inside is aggregating the matter. So we had the distribution, almost homogeneous distribution, but with an initial pattern of fluctuations. And now you see from nothing, you produce a network, which is very much like what I just showed you from the observations. And if you change the percentage of the ingredients that I told you are at the basis of our universe, so if you add more dark matter, for example, or more dark energy, or this doesn't work anymore. You don't get the right size of the voids. You don't get the right size of the filaments. You get something which is too homogeneous, less homogeneous. And so it's one of the pillars. These measurements of the large-scale structure is one of those things that, together with the supernovae, they agree perfectly. That's the great thing. The standard model of cosmology today is also called the concordance model. Okay, now we are going to finish. So is this the only explanation? Well, maybe not. Maybe we are not understanding general relativity so well. We are applying it not completely well. That might be an option. Or maybe on large scales, general relativity is not yet complete. Maybe we need to generalize it further. And although this is very, very disturbing, because general relativity is such an elegant theory that modifying it looks a bit like a sacrilege. And so far, all tests of general relativity have confirmed it. You know, there are many reasons why general relativity is a bit of strange theory, but because it cannot be quantized, but this is another problem. It is a bit an odd with quantum theory, so you don't really know what happens when you go to very small scales with gravity. But the only way to understand things better is to take more data, do more experiment, and just mention Euclid, which is the next generation cosmological mission of the European Space Agency, that in Milan we are very much involved, and the launch is approaching. It's very close, actually. It will be in well, less than 2 years. It's approaching very fast, and the telescope is actually ready. This is a real picture. This is Euclid in the clean rooms of the Thales Alenia Space in Turin, and it's quite amazing to see it live, I can tell you. And well, work is going on with the very last tests. We have a little problem with one of the instruments at the moment, but we are going to solve it, and this will be very, very interesting when it goes. So it's a universe with a lot of mystery, and I leave you with these words by Albert Einstein, and just reminding us that the universe is full of mystery, and mystery is the most fascinating feeling that human beings can probably experiment. And for Einstein, I just translate for those who do not read Italian, but basically Einstein saying that he cannot understand, or at least he feels pity for those that do not know the emotion of feeling the mystery that is around us. So I thank you very much for hearing, and well, it was a bit long, but I hope you enjoyed it.
Thank you very much, really. Thank you, Professor. So I'd say it's time for questions for all of you who are following both on the 2 pages. Just comment below the video with all the questions you want to ask. We already have one, which is just a brief clarification about what is exactly dark matter. Dark energy. What do we know about dark energy? Is it convertible in other types of energy, hypothetically? Is it not?
We know absolutely nothing or very little about dark energy. We call it dark energy. In fact, for what we know at the moment, this is only a constant in the equations of Einstein. So, you know, when you have differential equations, which I don't want to be complicated, but perhaps you heard about differential equations. When you integrate them and you find solution for these equations, you can add constants because those constants will go away when you put them into the equation. So you have this freedom, and this constant could be 0. And Einstein at the beginning put it 0, and then he put it different from 0 because he wanted to stop the universe. And today we find out that this constant is non-zero. And why has this value? We don't know. It's a complete mystery. This is actually this is a difficulty. It's a difficulty for the theory because you would like to have an explanation. Actually, the way this constant behaves is the same way, is the same effect you would get if the vacuum, if vacuum had an energy. Well, we know that vacuum has an energy. Quantum, in a quantum sense, vacuum has an energy. You cannot say that in a position in space you have 0 energy, because for Heisenberg, in the determination principle, you always have to admit fluctuations of energy in every place. And this actually has been measured. The Casimir effect is an effect which reflects this. However, if this was the case, if the cosmological constant had to be proportional to the quantum energy of vacuum, then it would be many orders of magnitude larger. So the common wisdom before these observations showed that there must be something that behaves like a cosmological constant. I said 20 years ago. Before, the conclusion of the physicist was, well, if there were a cosmological constant, it would have been very, very big, and we would have seen the effects. Since we don't see the effects, then it's zero, okay? And in fact, we find it non-zero, but very small. How small? Well, that's the other problem. It's small and is of the same order of magnitude of the density energy in matter. Dark or normal, doesn't matter in this moment. And that's also quite strange because actually today the density of the two things is comparable. So in terms of a scale that we use in cosmology, well, you can also say in this way, dark energy is 70%, matter is 30%. If you let the universe expand 2 times, to expand the radius 2 or 4 times, so in the future, you will find the matter counting for 5% and the cosmological constant 95%. If you go into the past, the cosmological constant has no effect. It was only matter dominating. So the question is why we are living today, where we are in this special epoch today, in which these two contributions are comparable. It's a bit strange. And so this stimulated theories that so-called that postulate a so-called dynamical dark energy. That means something which today is a constant, but in the past was not a constant. Something that started with a different value and then converged to the value that we see today. And this is the remit of theoretical physics, and you can think of specific fields, specific scalar fields that behave like a cosmological constant when they come asymptotically to the current epoch, and that's one possible explanation. And to see that, we must be able to do our measurements very far away to high precision. And this is one of the things. This is exactly one of the questions that Euclid wants to answer. So, is the cosmological constant a constant, or is it a scalar field or whatever?
And Omar, thank you very much indeed. Thank you from me as well. So I don't see any other questions as of now. So I'd say that we might conclude. And
okay.
I really thank you again. I think that Gerd wants to have a couple of final words to thank you as well.
Yep.
I have to say thank you for this interesting lectures. Thank you because we learned many things about the universe, about our knowledge of how the universe does work. I say thank you to Granada. Giovanni, it was a pleasure. But the most thanks goes to you, everyone who participated in this streaming, this first live streaming event, and see you the next time. Thank you very much.
Okay, okay.
Good night.
Good night. Thank you, Gerd. Thank you, Giovanni. And see you soon in the future. All the best to everybody. Stay safe and through the Christmas festivities. Have a safe Christmas. We have to say this year.
Thank you.
Thank you again.
Stay safe.
Bye, Gerd.
Bye.
Ok, abbiamo interrotto